have this function y equal to sine cube x minus 6 sine squared x plus 11 sine x minus 6. And we want to be able to figure out the range for this function. Obviously, all values of x are acceptable, but then sine x would always be numerically less than 1. Based on those considerations, let's figure out how this function y behaves, right? First things first, just out of ordinary algebraic simplification, we take sine x equal to some t. So then y becomes a function of t cube minus 6t squared plus 11t minus 6, right? Y dash is 3t squared minus 12t plus 11, right? Now this y dash versus t is an upward opening parabola. It's an upward opening parabola. And realize that the discriminant of this 144 minus 132 root 12 is greater than 0, right? That means it has two real roots. The two real roots of this two plus minus 1 by root 3, 2 plus 1 by root 3 and 2 minus 1 by root 3 are the two roots for this. So then y dash t versus t is a graph like this. Y very clearly t equal to 2 will be the line of symmetry because 2 plus 1 by root 3 is a root and 2 minus 1 by root 3 is a root. So this is 2 plus 1 by root 3 and this is 2 minus 1 by root 3, right? Okay. But now the relevant values of t are those that are less than 1 and greater than minus 1, right? This is t slightly greater than 1, right? So t equal to 1 will lie somewhere here, t equal to minus 1 will lie somewhere here. Now, when t lies between minus 1 to plus 1, y dash t is positive. Do you realize that? For t belonging to minus 1 to 1, y dash t is positive. Y dash t is positive, isn't it? This is y dash t versus t, right? That means in this interval, yt is an increasing function of t, yt is an increasing function of t. So, in the interval minus 1 to 1, yt increases monotonically, yt increases monotonically, right? And therefore, if it's increasing monotonically, it assumes the least value at minus 1 and assumes the largest value at t equal to plus 1. And therefore, the range of the function is y at t equal to minus 1 to y at t equal to plus 1. This would be the range. Y at t equal to minus 1 and y at t equal to plus 1. That's going to be the range because it's monotonic in that interval. Clear? Whatever you get out of this. Shall we proceed then? How many of you got this right? By actually working it out completely and not making guesses y minus 1 and y plus 1. In a situation of this kind, there is good amount of probability that you get it right without actually doing it right. That's the reason I thought, it will be useful for me to clarify how you got it. PQ are prime numbers. Again, both small p and small q, right? Courtesy Animesh da. This p looks bigger than it should be. PQ are prime numbers, and the equation PQ are prime numbers, and the equation x squared minus px plus q equal to 0 has distinct integer roots, So alpha beta are the roots, integers. So alpha into beta is q. Q is a prime number. That means one of the roots must be q, the other must be 1. One of the roots must be q, the other must be 1, because q is a prime number and alpha beta are integers. So then, let's say one root alpha is q, the other root beta is plus 1. And now the sum of the roots, alpha plus beta, is q plus 1, and that must be equal to p. That means p and q are consecutive primes. P minus q is 1. That means p and q are consecutive primes. So one must be 2, the other must be 3. Isn't it? P minus q is 1 and p and q are primes, and they are consecutive primes. That means one must be 2, the other one must be 3. So let's say p is 3 and q is 2. And then the rest follows. Clear? fx. Let fx be a twice differentiable function in the interval a to b, given that fx and f double dash x has the same sign in AB. That means fx into f double dash x must be greater than 0. Fx into f double dash x must be greater than 0. They have the same sign, either both positive or both negative in the interval a to b. F dash t equal to 0, f dash x equal to 0 has at most one real root in AB. That's a statement. And statement 2, an increasing function can intersect the x-axis at most once. Now think of a function gx, which is fx into f dash x. Think of a function gx, which is fx into f dash x. Then what's g dash x? G dash x is f dash x whole squared plus fx into f double dash x. Now that's the reason we constructed a function of this kind, because now fx into f double dash x is greater than 0 and f dash x whole square is greater than 0. That means this is greater than 0. That means gx must be an increasing function of x. That means gx must be an increasing function of x. Okay. Now if gx is monotonically increasing in a to b, then gx can have at best one root in a to b. What's the best possibility? If I have a function, continuous function, monotonic in an interval a to b, then it can have at best one root in the interval a to b, call it x naught, right? Isn't it? No, but then this is strictly greater than 0. This is strictly increasing. Tell me how else could it have been? Tell me what else could have been the graph of dx. Now, once this is the case, this function fx into f dash x can vanish at only one point, x naught. That means f dash x for sure cannot vanish at more than one point, because if f dash x vanished at more than one point between a and b, then gx will have more than one root in the interval a to b. So f dash x cannot be equal to 0 for more than one value of x in the interval a to b, because if that was the case, then gx would also vanish at those many points. But gx is vanishing only can vanish at best at one point. That means f dash x can become 0 in the interval at best at one point. And what's the reason? The reason is this: an increasing function in an interval can have at best one root in that interval. So statement 1 is true, and statement 2 is really the reason that guarantees statement 1. Yes or no? So there is a plus x plus 2. Sorry. Right? F of g of x. F of g of x. First of all, so we want to figure out the local minimum for f of g of x. Evidently, we are then talking of f dash. We are talking of ddx of f of g of x. A local minimum would be encountered at a point where this becomes 0. ddx of f of g of x becomes 0. F of g of x. So this is f dash g of x into g dash x. So then the local minimum of f of g of x is about a point where g dash x becomes 0 or a point where f dash gx becomes 0, right? Now let's look at this. F dash x is x squared plus x plus 1, right? Which you know is like a x plus half whole square plus 1 by 4, which will always be greater than 0, right? That means f dash x is always greater than 0. That means fx must be a increasing function of x, fx, right? In any case, f dash of anything is greater than 0. That means f dash of this is never becoming 0. F dash of anything, that anything could be g of x or could be anything, right? So f dash of anything is greater than 0. That's what we have arrived at. That means this is never becoming 0. That means the local minimum of this is about the local minimum of g dash x. The local minimum of g dash x, the local minimum of gx will tell you the local minimum of f of g of x. So we're talking of points where g dash x becomes 0. So g dash x equal to 0 is about x cubed minus 6x squared plus 11x minus 6. That's g dash x, which you know is x minus 1 into x minus 2 into x minus 3. I mean, this is out of inspection because this is 1 plus 2 plus 3, the sum of the roots. This is 1 into 2 into 3, and then you know that you don't have to check for this. Chances are that this will be like 1 into 2 plus 2 into 3 plus 3 into 1 would be 11, right? So in any case, g dash x vanishes at x equal to 1, 2 and 3. So as far as the sign of g dash x is concerned, this is the wavy curve for g dash x, right? Now, to the left of x equal to 1, g dash x is negative. To the right of x equal to 1, g dash x is positive. So x equal to 1 must be a local minimum for gx, because the first derivative changes from negative values to positive values around x equal to 1. So x equal to 1 is a local minimum. And then look at 3. To the left of x equal to 3, g dash x is negative. To the right of x equal to 3, g dash x is positive. At x equal to 3, g dash x is 0. So x equal to 3 must be a local minimum. So the local minimum of gx are 1 and 3, 2 points, and those would also be the local minimum of f of g of x. Got me? All right. Problem 5. G of x is a naught plus a1x plus a2x squared plus a3x cubed, and f of x is square root of g of x. Fx has its non-zero local minimum and maximum, local minimum of g of x at x equal to minus 3 and local maximum at x equal to plus 3. A3, one of the coefficients of gx, belongs to the domain of the function sine inverse 1 plus x squared plus by 2x. Or essentially you need to find the coefficients a naught, a1, a2, a3, etc. Right? So we have gx defined like this. F of x is root gx, and g of x, which is a cubic, has a local minimum at -3 and a local maximum at x equal to +3. One of the coefficients a3 is the domain of this function. What's the domain of this function? Plus and minus 1, just two values of x, right? Just two values of x, +1 and -1. Yes or no? So a3 will belong to the set -1 +1. Is there anyone who wants me to describe why the domain of this is -1 and +1? So a3 would either be -1 or +1. Now go back to cubic days, where I told you, see, typically the graph of a cubic, ax cubed plus bx squared plus cx plus d. If this was a cubic, then the graph of this cubic, if a was positive, the graph of this cubic was like this, right? For a positive, this was the graph. And when a was negative, the graph was, this was the graph of the cubic. Do you realize that? When a was negative, the graph of the cubic started here and went this way. If a was positive, the cubic graph was like this. What's the difference between these two graphs? When a was less than 0, you had first a local minimum and then a local maximum. But when a was greater than 0, you had first a local maximum and then a local minimum. Yes or no? Are you there with me? Depending on the coefficient of x cubed, if the coefficient of x cubed was positive, then the graph of the cubic first gave to you a local maximum and then gave a local minimum if a was positive. But if a was negative, then you had first a local minimum and then a local maximum, right? Now for gx, the local minimum comes first and then the local maximum. See, for gx, the local minimum is coming first and then the local maximum. That means in gx, the coefficient of x cubed must be negative. Yes or no? Are you confused? So this must be the graph of g of x with a3 being less than 0, with a3 being less than 0. And if a3 is less than 0, that means a3 must be -1. Yes or no? a3 must be -1. Are you all there with me? So we figured out that a3 is -1 at least. a3 therefore is -1 because the local minimum is encountered and then a local maximum for the cubic gx. The next thing is g dash x has roots -3 and 3. G dash x is vanishing at -3 and 3. Now what's g dash x? G dash x is like a 3. This is a3 is -1, so -3x squared plus 2a2x plus a1. Putting a3 equal to -1, so -3x squared plus 2a2x plus a1. That's g dash x, and the roots of g dash x will be -3 and +3. So sum of the roots is 0, which would be minus b by a. So that would mean a2 is 0, sum of the roots, right? And the product of the roots, which is -9, must be a1 by -3. So a1 must be 27. A1 must be 27. No? Are you there with me on this? Sum of the roots 0 minus 2a2 by -3. So a2 is 0, sum of the roots being 0. Clear? So well, a1 plus a2. Now how about a0? Let's figure out the limitations on a0. We figured out a1 is 27, a2 is 0, A3 is -1. G of x is minus x cube. A2 turned out to be 27, is it? So 27, I'm sorry, A2 turned out to be 0. So, and A1 was 27, so 27x plus A naught. That's Gx. That's Gx, right? Now, what about A naught? What about A naught? Come down to this fx. This should be greater than 0. This should be greater than 0. Can you then figure out the range of A naught? You can figure out the range of A naught from the rest of the conditions. Are you there with me? Right? And then of course, f minus 10. F minus 10 means, this at minus 10, this at minus 10, this should be greater than 0. Put x equal to minus 10. So whatever it turns out to be, this must be greater than 0. And that will again give you the range of A naught. That again give you the range of A naught. Are you okay with this? How many of you solved this completely? The right way? Okay. Y equal to fx. Y equal to fx. R2R is an odd differentiable function. This is an odd differentiable function such that f triple dash x greater than 0. F triple dash x greater than 0. That means f double dash x must be an increasing function of x. That means f double dash x must be an increasing function of x, and g of alpha beta g of alpha beta is this. It's also given that f double dash g of alpha beta is 0. Okay. We need to find the value of sine square alpha plus sine square beta. We need to find the value of sine square alpha plus sine square beta. Hey, it's given that f is an odd differentiable function. If f is odd, f dash must be even, f double dash must be odd. Yes or no? Derivative of an even function is odd, derivative of an odd function is even. You know this, right? Now you know that. So, f dash will be even, f double dash would be odd. Now, not just that. F double dash x is an increasing function and it's odd. F double dash x is an increasing function and it's odd. Isn't it? F double dash x is an increasing function and it's odd. That means the graph of f double dash x versus x should look something like this, let's say. At x equal to 0, an odd function will be 0. At x equal to 0, an odd function will be 0 always, right? And it's monotonically increasing. So if f double dash becomes 0 at a certain point, then that point must be 0. If f double dash becomes 0 somewhere, and if f double dash x is increasing, then that point must be 0. That point must be 0 if it's increasing. That means, do you realize that g of alpha beta must be 0? If f double dash something becomes 0, given the characteristics of f double dash x, what are the two characteristics of f double dash x? Number one, it's odd. So if it's odd, it must pass through the origin. An odd function will always pass through the origin. Are you comfortable with this fact? And then it's monotonically increasing. That means it will not become 0 anywhere else except x equal to 0. That means if f double dash is becoming 0 somewhere, then this must be 0. Then this must be 0. That means g of alpha beta must be necessarily 0. G of alpha beta must necessarily be 0. G of alpha beta means this is 0. Right? Now, this we can simplify as sine to power 4 alpha minus 1 whole square right now. I hope I've not left you disturbed. Have I left you disturbed with this? No, no. And then if sum of three non-negative numbers is 0, then each must be 0. Each is 0 means sine squared alpha minus cos square beta equal to 0. Sine squared alpha minus 1 minus sine square beta equal to 0, or sine square alpha plus sine square beta equal to 1. Got me? How many of you got this right? Very good. Very good. By the way, that was problem 6. Can I wipe this off? Yeah, your attention please. Fraction part. X fractional part of x and twice box x. X and fractional part of x are segments of a focal chord of an ellipse. Let's say if this is one of the foci, then this is x, this is fractional part of x, and this is the length of the lattice rectum. That means the semi-lattice rectum is box of x. The semi-lattice rectum is box of x. Now, recall one of the properties of an ellipse. X, fractional part of x, and box of x. In fact, box of x is the harmonic mean between these two. Box of x is the harmonic mean between x and fractional part of x. Yes or no? You recall this property? So, box of x is twice x into fractional part of x divided by x plus fractional part of x. Okay. Obviously, x is a positive number. X is a positive number. X into fractional part of x is less than x because fractional part of x is less than 1 and this is greater than x. So, this ratio is less than 1. So, this is less than 2. This is less than 2, yes or no? Are you there with me? This is less than 2 and box of x can either be 1 or it can't be 0. Can it be 0? So, box of x in this case is 1. Box of x must be 1. Right? Now, box of x is 1, which is the semi-lattice rectum, which is b squared by a. B squared by a is the semi-lattice rectum, that's equal to 1. That's equal to a into 1 minus e squared, and that's equal to 1. So a is 1 by 1 minus e squared, which is greater than 1, because 1 minus e squared is less than 1, so this is greater than 1. So the major axis to a is greater than 2. The major axis to a will be greater than 2. Got me? Right, bro? Now, fx is this. So f dash x is like a fx whole square, which is greater than 0. That means fx must be an increasing function of x. Fx must be an increasing function of x. Now, this is differentiable at x equal to a. This is differentiable at x equal to a. The derivative of this is f dash gx into g dash x into g dash x, right? Into g dash x. Now, the important thing is f dash gx is always greater than 0. F dash of anything is always greater than 0. So f dash gx is always greater than 0. It's never equal to 0. It's never equal to 0. See, f dash of anything is greater than 0. So f dash of gx will be greater than 0. Now, evidently, then, if gx is not differentiable, if gx is not differentiable, then this will be not a differentiable function. This will not be a differentiable function at x equal to a. See, at x equal to a, we have f dash ga into g dash t. G dash t. See, gx, one thing, it's not like the, see, for f of gx to be differentiable, this has to be continuous. The derivative continuous means the function differentiable. If the derivative function is continuous, this is the derivative function, if this is continuous, then this must be differentiable. Is that all right? If the derivative function is continuous, then this must be differentiable. This is the derivative function. If this is continuous, then this. Now, so essentially we are talking of continuity of this product of two functions. It's possible that this is discontinuous at x equal to a. This is discontinuous at x equal to a. In fact, it's possible that g dash x is discontinuous at x equal to a, and yet the product could be continuous at x equal to a, provided this becomes 0. Provided this becomes 0. If you have a product of a continuous and discontinuous function at a certain point, let's say, this is very important to understand. Let's say this is a continuous function. At x equal to 0, this is a continuous function. And you have a function which is, say, discontinuous at x equal to 0. Then the product of this function and this function, let's say this kind of a function. A function like this is one function and this is another function. At x equal to 0, realize that this function is discontinuous, but the value of this function is 0 at this point. So if you had looked at the product of these two functions, then at x equal to 0, the product would have been continuous. You can have the product of a continuous and discontinuous function at a point, still a continuous function, if at that point one of the functions is 0. If you have a product of two functions, I repeat, if you have a product of two functions, and if at a point one of the functions is discontinuous, then the product can still be continuous. The product can still be continuous if the other function at that point becomes 0. For example, if you had like a y equal to x box x, which is what I was attempting to give to you, then at x equal to 0, box of x is discontinuous, but at x equal to 0, this is continuous. But at x equal to 0, this becomes 0. So then x of box x, despite box x being discontinuous at x equal to 0, x of box x is continuous because the product becomes 0 owing to one of the functions becoming 0. So the product of a continuous and discontinuous function at a point can be a continuous function at that point if one of the functions is 0. You know what I'm saying? So now we have this product. In this case, this is never becoming equal to 0 because f dash is greater than 0. Which means for this to be continuous at x equal to a, it's extremely mandatory for this to be continuous. That means g dash k must exist. Because if g dash k does not exist and this is greater than 0, then at x equal to a, this will be discontinuous. You know what I'm saying? Because if this were to be 0, then g dash x at x equal to a may not have existed, may not have been continuous. G dash x at x equal to a may not have been continuous and the product would still be continuous. But the very fact that this is never equal to 0 at x equal to a, g dash k must exist. That means gx must be continuous at x, g dash x must be continuous at x equal to a, or gx must be differentiable at x equal to a. Gx must be differentiable at x equal to a. Are you all there with me on this? So it's a mandatory requirement that gx be differentiable at x equal to a, because f dash is not becoming 0 at x equal to a. So, got me? Gx must be differentiable at x equal to a because this is not becoming 0 at x equal to a. For this to be continuous at x equal to a. Got me? Now, realize that box of 2x minus 1 would be discontinuous at all those values of x for which 2x minus 1 is an integer, right? Now, when x lies between minus 3 and minus 1, 2x minus 1 lies between minus 7 and minus 3. Yes or no? 2x minus 1 lies between minus 7 and minus 3. That means 2x lies between minus 6 and minus 2. 2x lies between minus 6 and minus 2. Now, the important thing is, what are the integral values between minus 7 and minus 3 that 2x minus 1 assumes? The integral values that 2x minus 1 assumes are minus 6, minus 5, minus 4. These are the integral values that 2x minus 1 assumes, right? And that happens for what values of x? That happens for x equal to minus 5 by 2, minus 2, minus 3 by 2. At these values of x, 2x minus 1 becomes an integer. That means at these values of x, box of 2x minus 1 is not continuous. At these values of x, box of 2x minus 1 is not continuous, right? Now, g of x is continuous everywhere. G of x is continuous everywhere. It's a cubic with a having a unique value. Now, if you want this product to be continuous at x equal to c, see, let's say this is some x equal to x naught. If you want this product to be continuous at x equal to x naught, for example, then gx must vanish at x equal to x naught. Then, despite this being discontinuous at x naught, this product can still be continuous at x naught provided g of x naught is 0. Are you there with me? The product of a continuous and a discontinuous function could be a continuous function if the continuous function vanishes at that point, right? So, for example, at x equal to minus 5 by 2, this is discontinuous. But if gx vanishes at x equal to minus 5 by 2, then the product will still be continuous. Alright? Well, so for this product, in any case, there are three prospects for discontinuity. This and this. But a has just one value. A has just one value which can be obtained if gx would either vanish at this point or gx vanishes at this. I mean, to reduce the number of discontinuity points of this, right? This can have at best 3 points of discontinuity in the proposed interval. What's the minimum number of points of discontinuity that it could have, the product could have? That's the question. Well, it depends on the value of a. If a is such that this vanishes at x equal to minus 5 by 2, then this will not vanish at minus 2 or minus 3 by 2. Yes or no? That means gx will vanish either at this point for a given a, or at this point, or at this point. That means it can reduce the number of points of discontinuity by at best 1. Right? Gx. If it vanishes at this point, then you get a unique value of a. Then that's fixed. Then gx will not vanish at this value of x. Because if it vanishes at this value of x, you will get another value of a. But a is a fixed number for a gx. Right? So gx of these 3 points can salvage pride in only one of the points. Right? Either this or this or this. So if gx, let's say, vanishes at this point, then x equal to minus 5 by 2 will not be a point of discontinuity of this, because gx is vanishing. Right? But if it is vanishing at this point, gx will not vanish at these 2 points, because that will happen for some other values of it. So that means the minimum number of points of discontinuity of this possible is 2. Either it will be discontinuous at this, and so on and so forth. So the minimum number of points of discontinuity of this function is 2. Of these 3 points, you can redeem pride in only one by causing gx to vanish either at this or at this or at this. Gx couldn't have simultaneously vanished at all these points, causing the product to be continuous at all of them, because a is a fixed number. Once determined by, let's say, this point, then you can't have another value of a for this point. Gx is a fixed function. Right? Are you all there with me on this? How many of you got this right? Oh, very good. Very good. Very clearly, gx is a quadratic polynomial. Any quadratic polynomial, you realize, can be written as g0 plus x g dash 0 plus x square by 2 factorial g double dash 0. We buy this argument first. The ABC in a quadratic polynomial are these only. If gx is a quadratic polynomial, the constant term must be g0. This must be, when you differentiate that, you get this, and put x equal to 0, you get this. When you differentiate twice and you put x equal to 0, then you get the coefficient of this. Yes or no? Do you realize this? Any quadratic polynomial can be written as g0 plus x g dash 0 plus x square by 2 factorial g double dash 0. Yes or no? Okay. So in this case, g0 is minus 6, g double dash 0, g double dash 0 is minus 2b. So we have gx is minus bx squared plus x g dash 0, that means plus cx, and plus g0, which is minus 6. That's gx minus bx squared plus cx minus 6, right? hx is f dash x. hx is another function. hx is f dash x, which is like 4x power 4 minus ax cubed. That's hx. That's hx. Clear? And then there are two curves, gx and hx, that intersect. Gx and hx that intersect at 4 distinct points. That means hx minus gx must have 4 distinct roots. hx minus gx must have 4 distinct roots, real roots, 4 distinct real roots. So hx minus gx is like 4x power 4 minus ax cube plus bx squared minus cx plus 6. That's the function hx minus gx. It's given that this function, this polynomial, has 4 distinct real roots, x1, x2, x3 and x4. It's also given that summation I by xi, I equal to 1 to 4, is 8. And ABC are all positive real numbers. ABC are all positive real numbers. Okay. If A, B, C are all positive real numbers, look at hx minus gx. Change of sign. 1 change of sign, 2, 3, 4 change of sign. That means it has either 4 positive real roots or 2 or 0 positive real roots. Right? Descartes' rule of signs. Descartes' rule of signs. Now, if you replace x by minus x, that means, this is the function Lx. If you looked at L minus x, then that's like a 4x power 4 plus ax cube plus bx squared plus cx plus 6. No change of sign. That means no negative real roots. That means no negative real roots. And all roots are real. All roots are real. That means if it has no negative real roots, all the 4 roots must be positive and real. All the 4 roots must be positive and real. Yes or no? That means these x1, x2, x3, x4 are all positive real numbers. Are all positive real numbers. Is that all right? So, xi's are all positive. Xi's are all positive. And I by xi, that is like 1 by x1 plus 2 by x2 plus 3 by x3 plus 4 by x4. What's the arithmetic mean of these? This by 4 equal to the arithmetic mean of 1 by x1 plus 2 by x2 plus 3 by x3 plus 4 by x4 is 2. That's the arithmetic mean of these. What's the geometric mean of these? The geometric mean of these is 4th root of 1 by x1 into 2 by x2 into 3 by x3 into 4 by x4. That's the geometric mean of these. Yes or no? Hey, but what's x1, x2, x3, x4? The product of the root is 6 by 4. The product of the roots is 6 by 4. Yes or no? So x1, x2, x3, x4 is 6 by 4. So if you plug in 6 by 4 here, 96, 16, 4 through 2. That means arithmetic mean becomes equal to the geometric mean. That means all numbers must be equal. That means 1 by x1 must be equal to 2 by x2, must be equal to 3 by x3, must be equal to 4 by. If the numbers constituting a AM and GM are positive, and if AM becomes equal to GM, then the numbers must all be equal. 1 by x1 must be equal to 2 by x2, must be equal to 3 by x3. Yes or no? And once you have all of these, you have the product of the roots available. Product of the roots is 6 by 4. So then all x1, x2, x3, x4 can be computed from these, right? Because each will be equal to the fourth root of the product. Each will be equal to this into this into this into this. Fourth root of this. If A equal to B equal to C equal to D, then each will be fourth root of ABCD. Fourth root of the product of these. But the product of these we already know. Fourth root, and this is 2. So each is equal to 2. So x1 is known, x2 is known, x3 is known, x4 is known. All roots are known. Sum of roots is known from sum of roots. Sum of roots is minus a by 4. So a is known. Sum of the product taken 2 at a time is known, which will be b by 4. So b will be known, c will be known, and so on and so forth. Everything is known to you. x1, x2, x3, x4, etc. Are you all there with me on this? A is an integer, and box sin x whole square plus sin x is 2a, which is an integer. We need to find the number of integral values of a for which this becomes commensurate. Easy to see that the right hand side is an integer. Box sin x whole squared is an integer. So sin x must be an integer. Now, sin x is an integer. That means sin x can assume values like 0, plus 1 and minus 1. So acceptable values of sin x are 0, plus 1 and minus 1. Not only that, if sin x is an integer, then box of sin x will be equal to sin x. Sin x is an integer, then box of sin x for these values of sin x will be equal to sin x, right? So then you have like a replacing both sin x by sin x into sin x plus 1 equal to 2a, right? Volume. Hello, can you hear me now? Hello? Yeah, okay. Evidently then, if you put sin x equal to 0 or sin x equal to minus 1, sin x equal to 0 or sin x equal to minus 1, you get a equal to 0 as one of the values. And then sin x equal to plus 1 will give you a equal to plus 1. If you put sin x equal to plus 1, you get a equal to plus 1. So two acceptable values of a, 0 and 1. Two acceptable values of a given the conditions are 0 and 1. Clear? Minimum of x1 minus x2 whole squared plus 12 plus root 1 minus x1 whole squared minus root 4x2 whole squared for x1, x2 belonging to the set of real numbers. We need to find the minimum value of this expression given that x1 and x2 are real numbers. Now, it's easy. Realize that if I have a circle which is x squared plus y minus 12 whole squared equal to 1. If I have a circle which is x squared plus y minus 12 whole squared equal to 1, then any x on the circle, any y on the circle is actually root 1 minus x squared plus 12, right? Any y on the circle, call it y1. For a given x1, any y on the circle would be what? Would be such that y1 is 12 plus root 1 minus x squared, right? That would be any y1 on the circle, for example. Now, basically then, and if you have a parabola y squared equal to 4x, then for any given x equal to x2, the corresponding y on the parabola would be root 4x, commensurate with this. Now, imagine a circle which is like a x squared plus y minus 12 whole square equal to 1 and a parabola which is y squared equal to 4x and a parabola which is y squared equal to 4x. If you take any x1, y1 on this circle, on the circle where y1 would be this, and if you took x2, y2, any point on the parabola where the y2 for any given x2 would be root 4x2, you then realize that the distance between P and Q, any point on the circle and any other point on the parabola, the distance PQ, that is the PQ squared, is going to be x1 minus x2 whole squared plus y1 minus y2 whole squared. That's distance between any 2 points, one on the parabola and the other one on the circle. It's going to be x1 minus x2 whole squared plus y1 minus y2 whole squared, where the y1 on the circle would be corresponding to a given x1. The y1 is going to be 12 plus root 1 minus x1 squared, and on the parabola, the corresponding y2 for a given x2 would be root 4x2. So then what does this expression represent? This expression represents the square of the distance of any point on this circle and any other point on the parabola. Any point of the circle. So now you can have different x1, y1s on the circle and you can have different x2, y2s on the parabola. So then this PQ, depending on what x1, y1 and what x2, y2 on the corresponding circle and the parabola that you've selected, you want to minimize this distance PQ. We are talking of minimizing this distance PQ. This represents what? For different x1, x2, For different x1, x2, it represents the different distances PQ between points on the circle and points on the parabola, right? We want to find the shortest distance PQ squared. We want to find the shortest distance PQ, right? Now, very clearly, if this is a circle and this is a parabola, I want to identify P and Q such that PQ is the shortest distance available between the circle and the parabola. That's what. And that shortest square of that shortest distance would be the minimum value of this. Are you all okay with this idea? Right? So that's an equivalent problem addressed here. The circle and the parabola. This is a circle with center 0, 12 and radius 1, right? Let's say this is the parabola, y squared equal to 4x, y squared equal to 4x. Now the shortest distance between two curves will always lie along a common normal to the curve, That means we are talking the line of shortest distance PQ would be a normal to the circle, will also be a normal to the parabola. If it's a normal to the circle, then that PQ, that segment PQ, when extended, must pass through the center of the circle, right? So for sure, we are talking of a PQ like this. Whose line extended will pass through the center of the circle to accomplish normalcy with the circle, to become a normal to the circle. In addition, this PQ will be a normal to the parabola at a point. In this case, A is 1. So this is like a AT squared and 2T. AT squared, 2T is any other point. So Q you can always refer to as AT squared 2AT. A is 1 here. For this parabola, A is 1. So any point on the parabola is like a T squared 2T. So we are talking of a normal at a point T of the parabola. And we are looking at the prospect of minimizing PQ square. Clear? Now the slope of the normal at any Q is going to be minus T. The slope of this normal is going to be minus T. So then the equation of the normal at Q is going to be what? Y minus 2T equals minus T into x minus T squared. Right? And this must pass through the center of the circle. This must pass through the center x equal to 0 and y equal to 12. It must pass through x equal to 0 and y equal to 12. Such would be T. So put y equal to 12 and x equal to 0. You get 12 minus 2T equals T cube. Such should be T. And T cube plus 2T minus 12. That must be 0. Right? And from inspection, you can see that T equal to 2 satisfies this equation. From inspection, you can see that T equal to 2 satisfies this equation. Yes or no? So, you can factorize this. We know for sure T equal to 2 is a solution. T equal to 2 is a solution to this. And once I know T equal to 2 is a solution to this, then I know the coordinates of Q. The coordinates of Q would be 4, 4. Right? So then the required distance PQ is going to be the distance OQ minus the radius 1 unit of the circle. The required distance PQ would be OQ minus 1. OQ would be this distance of 0, 12 from 4, 4 minus the radius of the circle, that will be PQ, and we are looking at the corresponding PQ squared. Simple, right? So we are looking at this will be PQ squared, where PQ will be a common normal between the circle and the parabola given in the problem. Does it make sense to all of you? Find the positive interior values of A for which the equation x cube minus 3x plus box of A minus 1 has all roots real with 2 being equal. This is a cubic, and I want 2 of its roots to be equal, right? Now for a cubic, really, it's a cubic whose coefficient of x cube is positive, so it's going to start from the third quadrant. This cubic will commence from the third quadrant. Now for a cubic to have two roots real, two roots equal, and all three roots real, we must have the following. Either like this, in which case one of the stationary points is also it vanishes at one of the stationary. So it could either vanish at this stationary point, or it could vanish at the other stationary point, right? It either vanishes at the first stationary point or it vanishes at the other stationary point, and that would cause two roots of the cubic to be equal, yes or no, right? It means all that you need to do is identify the stationary point. The stationary points of this are 3x squared minus 3 equal to 0. So x equal to plus minus 1 are the two stationary points. That means either at x equal to plus 1 or at x equal to minus 1, not only is the derivative 0, but the value of the function should also be 0 to accomplish two equal roots at the point, right? So that means what we must have is either f1 0 or f minus 1 0. That means f of 1 into f of minus 1 must be 0. F of 1 into f of minus 1 must be 0. And f of 1 would be like a 1 minus 3 minus 2. So box of a minus 1 minus 2. That's f of 1. F of minus 1 is minus 1 plus 3, which is minus 2. Oh, sorry, 1 minus 3, so minus 1 plus 3, 2. Box of a minus 1 plus 2, that equal to 0, right? Which means either this is 0 or this is 0. That means either box of a minus 1 is 2 or box of a minus 1 is minus 2. When would box of a minus 1 be 2? When a minus 1 is greater than or equal to 2 but less than 3. Or when is box of a minus 1 equal to minus 2? When a minus 1 is greater than or equal to minus 2 but less than minus 1, right? When a minus 1 is greater than or equal to minus 2 but less than minus 1, then box of a minus 1 will be minus 2, right? So this or this condition, or we'll have to take this union this, essentially this or this or this, that will give me the required values of a. Either this could be 0 or that could be 0. Either f1 is 0 or f minus 1 is 0. In each case, you will get two equal roots and all three real roots. Yes or no? Is that okay? Then you can find the corresponding integral values of a in this interval, isn't it? In this case, for example, you get a greater than or equal to 3, less than 4. So 3 in this case, for example. So in that interval, look for the positive integers if they exist. Clear? We have f dashed x greater than or equal to fx whole square plus 1 by fx, and fx is a positive, continuous and differentiable function on the interval a to b, where this is fx whole cube, where it's given limit fx x tends to a from the greater than a side equals plus 1, limit fx x tends to b from the less than b side is 3 to the power 1 by 4. we need to find the maximum value of b minus a. Given these conditions, we need to find the maximum value of b minus a. Hey, very clearly, fx into f dashed x will be greater than or equal to 1 plus fx whole to power 4, multiplying throughout by fx without changing the sign of inequality, because fx is known to be positive. So the direction of the inequality does not change on multiplying throughout by fx. Is that okay? Now, fx into f dashed x by 1 plus fx to the power 4 is greater than or equal to 1, right? If one function is greater than another function, then the integral of one function in the interval a to b will be greater than or equal to the integral of the other function in the interval a to b, right? So integrate both sides. From a to b greater than or equal to a to b dx. Is that okay? Dx here also. Now realize that fx into f dash x dx is fx d of fx first of all, and t dt is d of t squared by 2. So this would be half of d fx whole square. How about it? Right? So this left hand side is half of a to b d of fx whole square by 1 plus whole square greater than or equal to b minus a. So b minus a will be less than or equal to this. That means this will be the maximum value of b minus a. Yes or no? This will be the maximum value of b minus a, and this is easy to integrate. So this is dt by 1 plus t squared, which is tan inverse t. This is dt by 1 plus t squared, which is tan inverse t. So b minus a less than or equal to half of tan inverse fx whole square. X changes from a to b, right, which is half of tan inverse fb whole square. Fb minus tan, that means 3 to the power 1 by 4 whole square, that is root 3, which is 60 degrees, pi by 3. So this will give me like a pi by 3 minus, and this was how much? 1. Okay. So at x equal to a, this will be tan inverse 1 pi by 4. So which is like pi by 24. So maximum value of b minus a is pi by 24. Maximum value of b minus a is pi by 24. Clear? X squared minus 6x plus 13 equals 4 times mod sine of a plus bx, where a and b are numbers that belong to 0 to 3. Find the maximum value of a plus 3b. Find the maximum value of a plus 3b. Now the left hand side can be written as x minus 3 whole square plus 4, right? And the right hand side is 4 times mod sine of a plus bx. Hey, the left hand side is always greater than or equal to 4. The right hand side is always less than or equal to 4. So the equality would occur only when both are equal to 4, and that would happen at x equal to 3. That means mod of sine a plus, put x equal to 3, must be 1. Yes or no? That means a plus 3b must be 2 n pi plus minus pi by 2, because this would be either plus 1 or minus 1. That means a plus 3b would be 2 and pi plus minus pi by 2, right? And a plus 3b, given that ab belongs to 0 to 3, will always be greater than 0, but less than 9 plus 3, 12, less than 12, right? Now, if you put n equal to 1, for example, then don't take the minus sign, take the plus sign, because we are looking for the larger values of a plus 3b, maximum value of a plus 3b. So if you put n equal to 1, 5 pi by 2. If you put n equal to 2, 4, 8, 9 pi by 2, and then there is a 7 pi by 2 if you take, and if you take the minus sign, you get 7 pi by 2. But 9 pi by 2, 9 pi by 2 will not fit the bill, because this is greater than 12. This is greater than 12. So that means the largest value would be 7 pi by 12. The largest value would be 7 pi by 12. That will happen when you take n equal to 2 and you take the minus sign here. 4, 8 minus 1, 7 pi by 2. That's the maximum value of a plus 3b, because that's less than 12. 9 pi by 2 would be greater than 12. Clear? 7 pi by 2 is therefore the greatest value of a plus 3b given the limitations. A function twice differentiable on a closed interval a to b such that fa is fb equals m, and for some alpha f alpha greater than m, where alpha is less than b and greater than a. The question is, does there exist an x naught? The question is, does there exist an x naught belonging to a to b, for which f double dash x naught is less than 0? Okay, so we have an interval a to b in which there is this function which is twice differentiable, fx, which is twice differentiable, and it assumes equal values fa and fb equal to m at the endpoints of the interval, and there is an alpha lying between a and b such that f alpha greater than m. Question to be addressed is existence of an x naught belonging to a to b for which the second derivative at x naught is negative, right? What we do is, well, between a and alpha, let's apply LMVT, right? In the interval a to alpha, let me apply Lagrange's mean value theorem. Which means that there must exist an x1 between a and alpha, for which f dashed x1 will be f alpha minus fa by alpha minus a. Right? There must exist an x1 for which f dash x1 is f alpha minus fa by alpha minus a. Hey, but fa is m given in the problem, and f alpha is greater than m. So this is positive. This is alpha greater than a because, right, it's to the right of the interval. So this is positive. There exists an x1 between a and alpha for which f dash x1 is positive, right? Okay. Now, between alpha and b, let me once again deploy Lagrange's mean value theorem, which means there exists an x2 between alpha and b. For which f dashed x2 would be fb minus f alpha by b minus alpha. Hey, but f alpha is greater than m, so this is negative, this is positive, so this is less than 0. F dash x2, where x2 is some number lying between alpha and b, which would be negative. Okay. Now, if you look at the function f dash x, because now we are talking of the second derivative of fx. So look at f dash x. for f dash x, there is x1 and x2 such that f dash x1 is greater than 0 and f dash x2 is less than 0. F dash x1 is greater than 0, f dash x2 is less than 0. So then, will there be an x0 between x1 and x2 such that the derivative of this, which would be f dash x0, will be f dash x2 minus f dash x1 by x2 minus x1. From LMVT, apply LMVT for f dash x in the interval x1 to x2. Can I not say that there exists an x0 such that the derivative of this function at x0, which is f double dash x, will be f dash x2 minus f dash x1 by x2 minus x1? That's applying LMVT for the function f dash x in the interval x1 to x2. Right? Now, f dash x2 is negative, f dash x1 is positive. So this is negative, this is positive, so this ratio is negative. So then there does exist an x0 between x1 and x2, which clearly lies between a and b also, for which f double dash x0 is less than 0. Does it make sense to all of you? We need to identify the number of real roots of fx from r equal to 1 to r equal to 2009. One thing for sure, that wherever f dash x exists, it's negative, because f dash x is minus r by x minus r whole square, r equal to 1 to 2009. So wherever f dash x exists, it will be negative. That means wherever f dash x exists, the function is decreasing. Wherever it exists. It does not exist everywhere. For example, at any x equal to r, fx is discontinuous, so f dash x does not exist at x equal to r, where r can be 1, 2, 3, etc. Yes or no? Are you there with me on this? So it's a decreasing function wherever the derivative exists. Wherever differentiable, this function is decreasing. It's decreasing. Clear? Now fx is like 1 by x minus 1 plus 2 by x minus 2 plus 3 by x minus 3 plus 2009 by x minus 2000. Right? Do you realize that x equal to 1 will be a vertical asymptote, x equal to 2 will be a vertical asymptote, x equal to 3 will be a vertical asymptote, and so on and so forth for this function? Right? There are 2009 vertical asymptotes for this function. There are 2009 vertical asymptotes for this function. Is that guaranteed? Right? That means, now if I have to tentatively draw the graph of this function, this is x equal to 1, this is x equal to 2, x equal to 3, in this way, x equal to 2009, etc. Now, when x is slightly greater than 1, this tends to plus infinity, right? This, and the rest are all finite, positive or negative, the rest will be all finite numbers. So that means this whole thing, when x is just slightly greater than 1, this whole thing tends to plus infinity. Is that okay? That means when x is slightly to the right of 1, it's plus infinity, right? Now, when x is slightly less than 2, this will be a negative number and minus infinity. This will be a, when x is slightly less than 2, this, when x tends to 2 from the less than 2 side, this tends to minus infinity, yes or no? And the rest are all finite numbers when x is slightly less than 2, right? That means when x is slightly less than 2, this whole thing tends to minus infinity. When x comes closer and closer to 2 from the less than 2 side, this tends to minus infinity. Is that okay? Right? That means to the right of 1, it's plus infinity. To the left of 2, it's minus infinity. And it's decreasing. Except at 1 and 2, where it's not continuous or differentiable, it must decrease. So then, it must be like this. between 1 and 2. And therefore, between 1 and 2, it must have a root x1. Yes or no? And the same stuff can be extended to 2 and 3. When slightly greater than 2, it's plus infinity. When slightly less than 3, it's minus infinity and decreasing. So between 2 and 3, there must be a root. Between 3 and 4, there must be a root. Between 2008 and 2009, there must be a root. Right? So then how many roots? Got me?